All right, so far this year, we have really focused on physics. We've done some stuff about motion, some things about energy. We studied sound waves, we studied light waves, and now we're going to shift from physics to chemistry. And there are some interesting things going on in the world that kind of connect what we studied about light to what we will study about atoms and molecules and other chemicals. So that's what this unit is all about, kind of merging from the study of light to the study of atoms and molecules, all right? So one example of that was the auroras, where we have these lights that are produced up really high in the atmosphere as a result of interactions between molecules, huh? We have these charged particles approaching us from the sun, and when they enter Earth's atmosphere, they follow the magnetic field, and they basically flow down around the poles. And when those electrified particles strike an oxygen atom, they make it glow one color, and when they strike a nitrogen atom, they make it glow a different color. So we get these amazing displays way higher than any clouds, right? Much higher than any clouds, 10 times higher than the clouds, up high in the atmosphere, in the north and in the far south around the poles. And we're going to talk more about how that happens in a little bit. And we're going to see some similarities between that and fireworks and between this lab we're going to do. And then we're going to move on and start studying. Actually, we're going to throw some astronomy into this unit too. And we'll learn a little bit about Saturn and the sun and Mars and Venus, based on the light that we can study and how it tells us about the chemistry of those planets. Okay, so the first thing, of course, that we always do is we remember to set up the comments so you can write in this. Personally, I like to get this whole thing out of my way so I can see it better. So I just click that. And then, of course, I have to remember to put my name in here. There we go. So why don't you go ahead and do that right now? Get your name going on. And actually, my expectation is that you put your name in two places on these, any assignment, really, whether it's a project or a regular assignment like the auroras. One, on the assignment itself like this, and two, right away, I'm going to save this. So I'm going to click File, Save As. And when this dialog box comes up, I expect you to add your name to the name of the file. So here it is, Unit 6 from Physics to Chemistry, and I'm just going to put my name at the end of that. I'm going to tell it where I want it to save. I think for my purposes, I'm going to put it on the desktop. I'm not sure what the best place is for you to save. But I do want you to add your name to the file. So why don't you just do that right now? Save it somewhere, add your name to the file name while you're at it. And so what we're going to be looking at here is this interaction between energy and matter. We're going to see how different kinds of matter give off different forms of energy. So kind of overlapping between physics and chemistry. All right. So if we look at the top, we can see the big idea for the entire unit. Every page repeats this big idea along with this main question for the unit, right? Just to remind us that these are what we need to focus on. Regardless of the activity that we do here, it should involve these ideas. First, that elements can be identified by the light they release. You can tell what element something is by the light that it releases. First of all, you have to add some energy to that element, and then it will release light. The way the aurora does that is by the charged particles in the magnetic field, huh? That's where it gets that energy from, the solar wind. Here in the lab today, we're going to use a Bunsen burner to add energy to these different chemicals and see what happens to the light that they emit as a result. And so then we have this big question: how can I analyze spectroscopic data to determine the composition of matter? First of all, composition means what something's made of, right? We're going to try to determine what matter is made of. How are we going to do that? We're going to analyze data from a tool called a spectroscope. Now, notice the similarity between that word and spectrum. We talked about the visible spectrum, the range of visible light, which is just a tiny part of the entire electromagnetic spectrum. All the different kinds of light, from radio wave to gamma waves. Visible light is its own little spectrum within that bigger spectrum, and we analyze those spectra with a spectroscope. So you guys know whenever you put scope on a word, it means that you're looking at something, huh? Like a microscope, you look at something very small. A telescope, you look at something far away. A spectroscope, you look at the different kinds of light, the different parts of the spectrum. All right? So let's talk about fireworks. What's it say? Please highlight, right? So grab your highlighter, or if you don't have a way to highlight, you can underline the important text as you go. Either way works, but that is part of your score. And I'm just going to read this out loud with you, and you highlight as we go, okay? Do we need to do the oohs and the woes and the ahs? I think you've all heard that before at a fireworks show, right? Kind of hard not to react that way. You've probably experienced the beauty and excitement of a fireworks display, but have you ever wondered how they make all the different shapes and colors? Isn't that what a scientist would do when they're watching something? Is wonder how it happens, why it happens, right? Or an engineer would wonder those things. Well, this is just one example of where physics meets chemistry. The following is an excerpt from Wikipedia's entry about fireworks. Fireworks were originally invented in China. Culture events and festivities, such as the Chinese New Year and the Mid-Autumn Moon Festival, were, and still are, times when fireworks are guaranteed sights. China is the largest manufacturer and exporter of fireworks in the world. The earliest fireworks came from China during the Song Dynasty, which was between the years 960 and 1279. Fireworks were used to accompany many festivities. The art and science of firework making has developed into an independent profession. In China, pyrotechnicians were respected for their knowledge of complex techniques in mounting fireworks displays. So, do you guys know what this root word pyro means? It means fire, right? So, doesn't that make sense? A pyrotechnician would be a technician of fire, right? They've learned how to manipulate fire in different ways. In regards to colored fireworks, this was derived and developed from earlier, I'm going to start over again. In regards to colored fireworks, this was derived and developed from earlier Chinese application of chemical substances to create colored smoke and fire, possibly during the Han Dynasty. Such application appears in 14th century writings, which describe recipes using low nitrate gunpowder to create military signal smokes with various colors. So they were using colored smoke to send signals to different parts of the army, right? If there's a blue smoke, you would do one thing. If there was a white smoke, you would do another thing, right? You could see that smoke from far away and almost instantly, right? So a good way to send signals. Later recipes from the 1700s include other chemical substances to tint flames and smoke. These included arsenical sulfide for yellow, copper acetate for green, lead carbonate for lilac white. What color is lilac? It's kind of a pale purple, yeah. And mercurous chloride for white. The Chinese pyrotechnics were described by the French author Antoine Caillot in 1818. It is certain that the variety of colors which the Chinese have the secret of giving to flame is the greatest mystery of their fireworks. The English geographer Sir John Barrow, around 1797. Hey, if you guys ever see this, like a date with a CA next to it, or it might spell out the whole word, CRCA, circa. It means approximately, or around, or about. So, for instance, there was a big flu pandemic in across the whole world, circa 1918. It was around 1918. Does that make sense? That's why this says CA 1797. We're not sure if it was exactly 1797, but it was close to that. At any rate, the English geographer Sir John Borlaug, around 1797, wrote, "The diversity of colors indeed with which the Chinese have the secret of clothing fire seems to be the chief merit of their pyrotechny." Fireworks were produced in Europe by the 14th century, becoming popular by the 17th century. Berthollet in 1786 discovered that oxidations with potassium chlorate. Now, this word oxidation is a type of chemical reaction. It's a chemical reaction with what other atom do you think? It's called oxidation. It's most likely oxygen, right? A chemical reaction with oxygen. Sometimes we have different names for an oxidation reaction. For instance, rust is a chemical reaction with oxygen. When iron turns reddish, when it rusts, that is an oxidation. Another example is burning something is a chemical reaction with oxygen. It's an oxidation reaction, which is probably the type of reaction we're talking about here for fireworks, isn't it? And what we're going to do here in a minute with these chemicals. So, Berthollet in 1786 discovered that oxidations with potassium chlorate resulted in a violet emission. Subsequent developments revealed that oxidations with the chlorates of barium, strontium, copper, and sodium result in intense emission of bright colors. The isolation of metallic magnesium and aluminum marked another breakthrough as these metals burn with an intense silvery light. So this is crazy. These metals actually burn. So you can buy something called, I don't know if you can, but for like a chemistry supply, you can buy something called magnesium ribbon. So imagine a thin um, piece of metal, kind of like foil, but it's flat. It's ribbon shaped, but it's metal. You can actually light it on fire, and it burns really brightly. In fact, it burns so brightly that it can damage your eye if you look at it for too long. So usually they don't let us use it in class anymore um, for that safety hazard. But it's an intense bright light that magnesium burns with. Modern colored fireworks were invented in Europe in the 1830s. Modern skyrocket fireworks have been made since the early 20th century. Okay? You see what you're going to do next down at the bottom? You're going to fill in that chart, right? You're going to find those different molecules in the reading. I think they're in two different places. Two different paragraphs describe these colors and name the color produced by burning these different molecules. Okay, so take a second to do that. No, it's all the stuff you just already read. Yeah, some of it's in here and some of it is further up there. Okay. Let's see if I have one. Oh, you're just gonna go grab yours. Yeah. Go. How are we doing? You finding them? This should be in two different paragraphs, right? Two different paragraphs should let you fill in that entire chart. Two paragraphs we just finished reading. Okay, give me a thumbs up when you're ready to go. How are we doing here? Ready? Thank you. You guys done in the back? Yeah? I think I'm going to assume that you guys are done at home too, all right? If not, come back to that on your own and get it finished up. Yeah. Better hurry. Just go. She's not in the restroom. All right, once again, we're going to do a little highlighting before we start the actual lab, okay? When elements are strongly heated, they produce different colored flames. These colors have a specific wavelength and frequency that are unique for each element. We'll discuss the details later, but you may remember that each atom has electrons orbiting around its nucleus. An electron can absorb energy when it's heated. And when this happens, we say that the atom is excited. That's an actual scientific phrase, is that the atom is excited. Later, the electron loses this energy, and that energy is then transferred to a photon, a particle of light. And that photon is behaving like a wave. It travels at the speed of light at a specific frequency and wavelength. So we see that photon as particular colors. So, for example, here's my nucleus of my atom, right? And it has electrons that are orbiting around it, correct? And when I heat the thing up, the electrons end up orbiting further away than they normally do. That's when they're excited. So normally they're orbiting in close. We heat it up, or it gets hit by an electrical charge, or somehow it gets excited and the electron goes to a more distant orbit. But it can't stay there forever. Eventually, it's going to fall back to its resting orbit. Does that make sense? When it falls back, it releases that energy that it picked up. And what form is that energy released in? Light. It's released in the form of light. And every element has a different wavelength, in other words, a different color of light that it will emit when it falls back from the excited state to, I don't know what they call it, the ground state. I just like to say that it relaxes or it calms down again, something like that, right? But because they used excited, so why don't we just say it goes back to the chilled state, right? I don't know. But we do use this phrase excited when it's up here, and then it relaxes again, goes back here. When it falls back to that ground state, it releases light, which varies with the elements. So we're going to look at these different flames using this Bunsen burner. I'm going to light this up, and we're going to take these wooden splints. They're just thin pieces of wood that I've been soaking in these different chemicals. We'll look at one first of all that hasn't been soaking, just so we know what color the wood is going to burn. And you pretty much know what color wood burns already, right? It's exactly what you would expect. But just so that we have a fair basis of comparison, since we're looking at the colors of the flames, we want to make sure things are compared correctly, right? Now, we do have some safety issues we have to deal with for two reasons. One, we have chemicals. Two, we have flame, right? And so we're all going to wear goggles. And the good news is the eye protection at this school is kind of cool. It's like ski goggles instead of those old kind of lab goggles. You know what I mean? So that's our first safety precaution. Second safety precaution is the person closest to the fire extinguisher needs to be ready just in case we have problems, right? Third safety precaution, person closest to the fire blanket. Like if my shirt catches fire, you got to run over there and throw that blanket on me, tackle me, cover me with the blanket, right? And put out the flames, okay? Ozzy, I'm counting on you. And then a couple other things is that I have a bowl of water up here. When I'm done burning something, I'm just going to toss the splint in the water. That should put it out. I also have a little spray bottle just in case I can spray out the water. And maybe we can use this instead of the fire extinguisher. I don't anticipate any problems, but we should always be prepared, right? Yeah. Okay. So let's get our goggles going. Oh, I guess Hugo has a different set. These are from the chemistry room. And I think what we're going to do is on the chart down here. So we're going to fill in this chart as we go, but for all we're going to do to begin with is fill in the two columns. First, formula. I'm going to give you the chemical formula for each of these as I burn them. Secondly, you will write down the color of flame that you see. All right, so you need to be able to see this Bunsen burner, and I want to make sure these guys can see it at home too. So if you need to move to be able to see this, let me know. Or just help yourself if you want to move to a better position. Okay, so I got to turn on the gas, and then I got to take the sparker. There we go. Now, Andres, will you turn off the lights for us? So can you see that okay? How about at home? I can't see it all. My glasses are immediately fogged up here. Yeah, you can see that, I think. So a Bunsen burner has two adjustments on it. One is the amount of gas coming through, and the other is the amount of oxygen coming through. And what we want is see, that's got a lot of oxygen. It's not burning very efficiently. We want an efficient flame that's basically pure blue and small. How's that? Pretty pure blue flame, pretty small. Now, if I take just a regular wooden splint that has not been dipped in a chemical, we expect it to burn with what color? Kind of a yellow-orange. Would you agree? So that's wood by itself. Okay? So on our chart, our first example is going to be copper chloride. Oh, I meant to do something else here. I'm just going to leave it. Okay. So on our chart, our first example is copper chloride, which its chemical formula, CuCl2. Now, really, the 2 is supposed to go down below the rest of the numbers. It's supposed to be a subscript like that. But I don't really care if you make it a subscript or not. It's a little bit of a pain the way we have this. But I do want you to get in the habit of always writing the symbol for an element with a capital letter. And if the element has a second letter, it is always lowercase. That way we can tell what these elements are. Cu is copper. It comes from the Latin word for copper, cuprum. Cl is chlorine. So this is copper chloride. And there are two chlorine atoms connected to one copper atom. So it tells us a lot just looking at the formula, huh? Right?
Mr. Fairley,
Yeah.
how are you putting in subscript?
I just made a separate text box and moved it where I wanted it to be. See?
Oh, okay.
Yeah. Now I'm going to disconnect from this meeting so that my flame shows up on this more completely. So I'm hoping that you guys can fill your screens at home with this flame so you can see what's going on a little better, okay? That's our goal, for you to be able to see it just as well as I can in here. So what was it? Copper chloride, right? Here we go. Watch the color of the flame. What color is it? Yeah, it's got that nice green flame, doesn't it? Yeah? Now, eventually I'm going to burn the chemical right off of there, and it's just going to start burning the wood. That's going to be back to that yellow-orange color, isn't it? Looks like it's kind of going from green to blue, doesn't it? Oh, now the wood's burning, huh? Copper chloride. Got that one? Next, we have lithium chloride, which is LiCl. LiCl, capital L and capital C. LiCl, lithium chloride. Are you ready? Here we go, LiCl. What color do you see there? Kind of cool, huh? So I've excited the atoms, right? This heat excites the atoms, and then when they fall back to their more relaxed state, that's when they release the light. And everything is its own different color. Okay, next, barium chloride, Ba. I think this is a Cl2. Let me double check. Yeah, this is a Cl2. BaCl2. BaCl2. Barium chloride. Capital B, capital C. Here we go. Ready? What do you say? It's a little yellower than the wood was, huh? But also a little tougher to tell the difference between the color of the wood burning and the color of the molecule, right? But I would agree, it's a pretty much of a yellow color. That one was BaCl2. Next, calcium chloride. CaCl2. Both C's should be capitalized. CaCl2. Here we go. What do we see there? Yeah, kind of an orange. It's pretty, again, it's pretty close to the color of the wood burning. But I think when the wood is burning, it's a little yellower than this, huh? There's the wood burning right there, huh? See the difference? It's a little yellower. Calcium chloride. Next, we have regular table salt, the stuff that you put on your food. Sodium chloride. NaCl. Now, sodium is, the symbol comes from a Latin word for sodium, natrium. That's why it's NaCl. Capital N, little a, capital C, little l. You ready? Here we go. Sodium chloride. Yep, it's pretty orange again, isn't it? In fact, that's harder to tell from the wood to me. Seems a lot like the wood color, but. Sodium chloride. Next, potassium chloride, which is KCl. Potassium is symbolized by the letter K, capital K, capital C, L, little l. Here we go. Potassium chloride. What color do we get now? Oh, do you see it in there? Yeah, it's a little bit purplish, a little bit violet, pale violet or lilac color. You ever seen a lilac bush? It's kind of that color. Or purplish. It's pretty pale though, huh? And then the last one we're going to do, strontium chloride. SR, capital S, little r, capital C, little l, 2. Strontium chloride. Here we go with the strontium. That's so bad. Looks like a sunset. Yeah, that's a pretty one, huh? And now the wood's burning, isn't it? Andres, you can turn the lights back on, please. Thank you. Yeah, you can take the goggles off now. Okay. So you guys should have filled in this column for formula and the column for flame color, right? And if you didn't, that's okay. We're going to take care of it right now. First of all, let's fill in their names. The full name of CuCl2 is copper chloride. Next, we had lithium chloride. Barium chloride. Notice all of these were different metals combined with chlorine. Then we have calcium chloride. Now we've left a little bit of space at the bottom. We're going to come back in a few minutes and we're going to do this backwards. I'm going to burn one of these splints, and by looking at its color, you have to tell me what element it is, what compound it is. A compound is a mix of things like these. Copper mixed with chlorine is a compound. Each of those by themselves is an element. The purest substance that you can find anywhere in the universe is an element, like copper or gold or oxygen. But you find them combined with other things, like when you mix oxygen with hydrogen, you get water. That would be a compound. Yes, sir. The last one is strontium chloride. SrCl2, strontium. It's a metal we might not be too familiar with. Thank you. All right, so you guys filled in the colors, right? What color did you get for copper chloride? Oh, by the way, sometimes it bugs me to have this showing. So if you hit those letters, it'll go away. And then if you want it back, you just hit it again, right? So copper chloride was green. So you already filled that in, huh? Next, we have to fill in these two final columns. To do this, first I have to refer to this chart. And what do I see? What's the wavelength? How many nanometers long is a wave in the green part of the spectrum? Well, that's yellow-green. I was just looking at straight green between 500 and 560, right? So I'm just going to choose a number in the middle of that. Unless I thought it was a little bluer, I might choose towards the bottom of the scale, towards the 500 side. If I thought it was a little yellower, I might choose 550, like that, right? If I just choose a number right in the middle, though, if I thought it was pure green, I would just say 530. So just choose a number in that range that you think fits, and we might have somewhat different answers here depending on what we remember that looking like. And then we have to do some math to find the frequency. And we're just going to use that same old equation from last unit, right here. The V equals F lambda, because V was the velocity, the speed of light waves. F was the frequency that we're looking for. Lambda was the wavelength that we are given by that chart, huh? So we do have to rearrange this a little bit. If I take, let me see, if I take a pencil, if I just take V equals F lambda, can I divide both sides by lambda? Cancel out the lambdas on this side, and I end up with V over lambda equals the frequency, which is exactly what I want, isn't it? Are you with me on that? I just used algebra to rearrange the equation. I went from V equals F lambda to F equals V over lambda, V divided by lambda. So I just have to divide the speed of light by the wavelength, by the lambda. So I'm going to grab a calculator. We're just going to use 3 times 10 to the 8th as our speed of light. So put in your calculator 3 and then 8 zeros. 3 times 10 to the 8th. And then divide by that frequency. Excuse me, divide by the wavelength. So 300 million, 3 with 8 zeros behind it, 300 million, divided by, what did I decide? I decided 530. And that gives me 566,037.7, 566, comma, 038. And that's measured in hertz. While this wavelength was measured in nanometers, a very short distance. So we're going to take a few minutes and I'm going to ask you to fill in the rest of the chart on your own. Use the chart above to decide what wavelength that light was, and then divide it into 300 million. Every time it's going to be 300 million divided by whatever number you chose for the wavelength. That'll give you the frequency. Okay? So just take a minute to fill all of that in. Yeah. Where's the point of the goggles? Well, what if something exploded over here? That was like the toxic air was getting. Nope, it's prevention. It's like put on your seatbelt. You don't plan to get in an accident, correct? So it's better to be smart than sorry. Yeah. Okay. You guys at home, give me a thumbs up when you're done with the chart. Okay, I think we're going to move on. Um, you're going to have some time to work on your own in a minute, so if you need to do some more math, you can come back to that. But right now, I want you to notice that I'm also asking you to write a title that describes what this table shows. Every graph, every chart, every table needs a good title, doesn't it? It should describe for the reader what it is that you're trying to demonstrate here. For example, you filled in a table a minute ago. I don't even know if you noticed that it had a title across the top of it, right? A pretty detailed title. Colors produced by different molecules when they're burned inside of fireworks. Does that tell you exactly what the table is showing? Did it include both parts of the table? Colors produced by different molecules. And what conditions we're using for them, huh? So a good title, a good scientific title, is going to be a complete sentence, and it will include the different variables involved. So if we go back to the table you've been working on, a good title is going to include something about, what do you think? What were we trying to show here? What were we comparing? We were comparing the colors made by what? We got to say something about color in our sentence, huh? Yeah, we got to say something about the material or the molecule in the sentence, right? Here I use the phrase compound, but you could say material or you could say molecule. And what else did we compare? Not just their color, but their wavelength and frequency, huh? So a good title would include all of those things in it. Something about the color and the molecule and the wavelength and the frequency. Can you put those ideas together into a sentence? I think for me, if I was going to write this one, I might start the title with a phrase that said something like a comparison between, and then I leave it to you to fill in the rest. What is it that we're comparing? Yeah, of what? Different compounds, huh? Right? So I want you to write it. I want you to write the rest of this sentence yourself. It should include something about color, something about the compound or molecule or material or substance, different words you could use there, huh? And something about wavelength and frequency should be included also. And you can list things with a bunch of commas, right? Could you say color, comma, wavelength, comma, frequency? And then you'd hit all three of them, wouldn't you? And then we're going to go back to our flame test. We're going to light up the Bunsen burner again, and we're going to turn off the lights. And I'm going to burn another chemical in here without telling you what it is. And then you go back to this chart to tell me what it is. All you have to do is fill in the chemical formula. You don't have to, and the color. You don't have to do wavelength and frequency on these, okay? Because these are just repeats of ones we've already done. But let's just see how well you can identify what it is by going backwards. Does that make sense? Okay. So we need to go goggles up again. Okay. Will you get the lights over there, Andres? Okay, here we go. Unknown number 1. Start by writing down what color it is, and then you tell me what formula it has. Here we go. What do you think? What color would you call that? Now we're getting into the wood.
Mr. Fairley,
Yeah.
we can't see it.
Not sure why. The flame is right here. It was kind of a reddish pink. Yeah, that's how you're going to tell me what you thought it was, is by writing down the formula. You don't have to give me the name, just the formula and the color. That's all you need. Unknown number 2. Here we go. Kind of a greenish blue, huh? Unknown number 3. Kind of a pale purple, violet, and blue. Okay, you can turn the lights back on, Andres. Thank you. So you should have written down their colors, like the first one was red. And then based on finding its color, go back to where we were over here and give me its chemical formula. For those 3 unknowns. And then after that, your goal today is to finish page 4. So we have a series of follow-up questions after the flame test. Looks like there's 8 of them. And I would like you to finish that before the end of the period, which is what, 20 minutes or so? Okay, so go ahead, finish up page 3 and 4. Whatever you don't finish is homework.